AI and cyber-physical systems are becoming more integrated into our everyday lives. Self-driving cars, medical devices, robotics, and other technology becomes increasingly automated. What protocols keep AI safe, reliable, and trustworthy? Will we be able to trust AI systems' autonomous actions? Join us as we hear from Sanjit Seshia, Professor of Electrical Engineering and Computer Sciences at the University of California, Berkeley.
So about a decade ago, we started thinking about what it would take to apply formal methods to cyber-physical systems that include AI and machine learning components. And what we realized was that there are unique characteristics of AI that make it difficult for traditional, even state-of-the-art formal methods to be effectively applied in that domain. And so we started to brainstorm about what challenges faced by formal methods in applying effectively to AI systems and what we can do to address them. Verified AI is the goal of achieving strong, ideally provable assurances of correctness and trustworthiness of AI systems with respect to mathematically specified requirements. As an example, think about an automatic emergency braking system in a modern automobile. In front of the car, you probably have a camera. The images captured by the camera go into something like a deep neural network, which is tasked with detecting objects and classifying them. And the output of that neural network then goes into a controller, which then actuates the various controls on the vehicle, and that moves the vehicle on the road. It interacts with its environment, and then that leads to new sensor data being captured by the camera. And so this is a closed-loop, intelligent cyber-physical system, and it's the kind of system that we want to be able to give strong assurances of safety. So for example, we'd like to be able to ask the question, is it always the case that when this car is in motion, it maintains a minimum safe distance from any other object in its environment? Given that cyber-physical systems are more and more around us and control various aspects of our lives, it's really crucial that we be able to give strong assurances of their safety and dependability and trustworthiness. So when we think about AI-based systems, the 5 main challenges that arise, first of all, start with the environment. So the environments in which these systems operate are very complex, and we don't even know how many or what agents and objects are in the environment, let alone have good models of how they behave. The second challenge is that the systems themselves are also very complex, partly because of the use of components like deep neural networks that have sometimes billions of parameters that determine how they behave. And then components like object detectors, which solve perceptual tasks, are hard to mathematically specify. Like, how would you specify that something is a picture of a car? And so even coming up with the inputs to the verification process is challenging here. But imagine that somehow you were able to get past that. Then the challenge of searching these extremely high dimensional input and state spaces is challenge number 4. And then finally, it's just much cleaner if we can do a clean slate design of the system so that by design it would satisfy the desired trustworthiness properties. But even that is an open question. How do you do correct by construction design of these systems? So to summarize, we identify these 5 challenge areas for verified AI. For each of them, we break them down into 3 specific challenges, and for each of them we identify one principle that we believe will be effective to address those challenges. And so this forms a 3x5 matrix, which is a lens through which we view this topic of verified AI. We survey the advances that have been made over the last 5 years, and we propose topics that we believe are important for the community to address going into the future.
Learn more in Toward Verified Artificial Intelligence, a contributed article in the July 2022 communications of the ACM.